let's go ahead and find area under this curve between x equals 1 and 4, bounded by the x-axis using the three methods: left endpoint rule, right endpoint rule, and midpoint rule. And we're going to construct three rectangles. So let's go ahead and see how the picture looks like. So even if you don't know how to graph it, that's totally fine, because you can just write down the real line and draw your x values. So here is 1 and here is 4. So you're finding area in this bound right here. So you don't really have to draw the entire picture. But I'm going to show it to you so that you can see which one is an underestimate, overestimate, or very close to the actual area. So let's suppose this is our xy plane. And 1 over x is a hyperbola. First curve is on the first quadrant, and the other curve is right here on the third quadrant. Now we're not looking at that, we're only looking at x equals 1 to 4. So let's say x equals 1 is here, and x equals 4 is right here. We want to know how much area is right here. That's what we're looking at. So first thing you want to do is draw it if you can. If you cannot, then just open a real line and plot the boundaries for the x values. Now we're going to create three rectangles. So you want to find what's the size of these rectangles. So there's three of them. So the width is determined by delta x. So this will tell you the width of each rectangles. And that is determined by simply subtracting the endpoint of the interval divided by the number of rectangles. And in this case, our interval we're looking at is 1 to 4. So think of this as your A, this is your B, and this represents the number of rectangles, that's n. So if you substitute that into this delta x formula, you have 4 minus 1 over 3, which will give you 1. So the size of each rectangle is 1. So from here to here, it's 1. So 1 plus delta x, that's 2. And then 2 plus delta x, that's 3. 3 plus delta x, that's 4. So that's what delta x represents. And now you're going to determine the height, but that's going to be determined by this curve right here. So depending on how you construct them and which method you use, your height are going to change. So let's focus on the left endpoint rule. So for the left endpoint rule, we're going to denote that as L for left endpoint. And because we're using three rectangle, you put a subscript 3 here. That means left endpoint rule with three rectangles. And the formula is simply area of a rectangle. So we know area of a rectangle is length times width. So in this case, our width is delta x. And our height is going to be determined by the function at some, let's say, x value. So let's talk about the left endpoint rule. So I'm going to construct the rectangle. So starting from here, I construct the rectangle right there. So the width, we know that's going to be 1, and the height is where it touches the curve. So that's where you're going to find that point. And the height is determined by the function at 1, because that's the endpoint of that rectangle. So you can call that one x1 if you want to simplify the notation. And then let's go to the next rectangle. So here's the next rectangle. So the height is determined by this point. That's going to be f of 2. You can call that x2. And then go to the next rectangle right here. So this height is determined by f of 3. You can call x3. So that's how you get the height of these rectangles. And you can see that these rectangles are a little bit over the curve right here. So whatever area you get, it's going to estimate a little over. So let's write down the formula formally. So we know the width of each rectangle, it's going to be delta x. And the height of the first rectangle is determined by f of x1. Plus the next rectangle, delta x is the width, height is f of x2. Plus the last rectangle, delta x is the width, and the height is f of x3. So that's how you set this up. And now let's plug in these numbers. So delta x, we know that's 1. Now if you want, since they all have delta x in common, we can factor that. to simplify the calculation. So this is delta x times the first height, the second height, and the third height. And now keep on going. So delta x, we know that's 1. And the first function value that we're going to determine the height is at 1. The second one is at 2. And the third one is at 3. Those are the input value. Now you plug them into the function. So the function is 1 over x. Plug in the x value into x. You get 1 over 1. So this is 1 over 1. Plug in 2, 1 over 2, plus 1 over 3. And then you simply add them up. This will give you 1 times 1 plus 0.5 plus 0.3. And then this is simply 1.83. So the area here is approximated to be 1.83. So that's the idea with constructing rectangles under a curve. Now let's go ahead and check out the other method. So we will do the same thing, but now we're going to be using the right endpoint rule. So I'm going to go ahead and take the picture and show you how to do that. Now we're going to be constructing same number of rectangles, but the height will be determined by different x values. I'm going to go ahead and erase these. All right, so now for the right endpoint rule, we're going to call that R, and because there's 3 rectangles, R sub 3. So now, first you're going to draw the rectangle. So we're going to draw the rectangle right here. Now the height is going to be determined by the right endpoint. So it's going to be this one right here for the first one. And for the second one, it's going to be determined by this point. That's the rectangle. And the last one, it's going to be this point. So that means this is your height for f of 4. This is the height for f of 3. And this is the height for f of 2. So you leave out this point. Whereas before we used that one, we left out 4. So you always leave out one of the endpoint. And you can see that this would be an underestimate because you're missing all of these little corners of the picture. So let's go ahead and do that. So let's call this one now x1, this one x2, and this one x3. When you plug them into your function, we can evaluate. So the formula, we know it's delta x times f of x1 plus f of x2 plus f of x3. So those are the height. And we know delta x is 1. And the first x value we're going to use is 2. The second x value is 3. The last x value is 4. And then you plug them into your function. The function is 1 over x. So it's 1 over 2 plus 1 over 3 plus 1 over 4. And then we try to see what this is. So this is 1 times 0.5 plus 0.3 plus 0.25. And the one we add them up, we get about, so this is approximation. So we can call this about 1.08. So you can see that this is a little underestimate, and you can see it from the picture. Here you can see this is an overestimate because the rectangles happen to be above the curve. Now let's illustrate the last method. So the last one is called the midpoint roll. So we're going to call this M, denoted by M for midpoint, and the number of rectangle 3. So this is going to be approximated by. Now here, looking at the same picture, let's reconstruct this, and I'll show you another picture. So for the midpoint rule, we don't need to use either the left or the right endpoint. You're going to use the midpoint of each subrectangles. So let me show you what I mean by that. So just still clearing this up. All right. So we know we're looking at from 1 to 4. That's the interval. And we subdivided that into 3 rectangles. So here are the subdivisions. Now for the midpoint, you're going to use the midpoint of each segment. So for the first rectangle, this is the midpoint. So whatever the midpoint is between these two, that's how you're going to determine the height of that rectangle. So that's the rectangle. The height will be the midpoint. So this is 2. So this height is going to be 2 plus 1 over 2. So it's the midpoint of that interval. And do the same thing for the next rectangle. This is the midpoint. Add them up and divide by 2. And this is the next midpoint. So this is going to be 3 over 2. So that's our first x value. And this is going to be 5 over 2. And this is 7 over 2. And now often we don't call them x1, x2, x3. We call them x1 bar. So we can call this one x1 bar because bar means the average. And then this point, we can call this x2 bar. And then the last one, we can call this x3 bar. So the heights are f of x1 bar. This height is determined by x2 bar. And this is f of x3 bar. So the formula is delta x times the height of each of these midpoints. So the first one is x1 bar plus x2 bar, and the last height is x3 bar. Delta x is again still 1 because it's the same problem, just different method. So the first midpoint we're using is 3.2. The next point is 5 over 2. The last one is 7 over 2. Then plug them into the function. So this is equal to 1 over 3 over 2 plus 1 over 5 over 2, and the last one over 7 over 2. So it's 1 over because the function originally it's 1 over x. So you're plugging in 3 over 2 into x right here. So it's like a complex fraction. And then if you reduce these, this will become 3. So 1 over 3 over 2, that's simply in decimal, that's about 0.66. And 1 over 5 over 2, that's about 0.4. And the last one, 0.28. And that is about 1.35. So now you can see that this is a little better approximation because the gap between the actual area and the estimated area is very small. You can see it right here. It's a very small gap. So often midpoint gives you a better approximation. Here, the right endpoint gives us a little underestimate. The left endpoint here gives us overestimate by a lot. Now, another thing to notice is you don't always have to do this. You can simply draw the number line. You don't have to draw the pictures. You can subdivide the interval 1 to 4. So 3 subrectangles. Then you know this is 2, this is 3. So for midpoint, you're taking this point, and that point. So you average them. This would be 3 over 2. This is 5 over 2, 7 over 2. Then you plug them into the function. So you can always draw this number line and subdivide the interval other than drawing the picture because sometimes you might not know how to draw the function. All right, so this is introducing us to integral, which we'll discuss in the next video. Stay tuned for that.